In this example, we're going to look at two current carrying lines where one current is going in this direction and the other line has a current that's going in the opposite direction. We'll call them both current I, so one's going up, one's going down. They're separated by a distance d and vacuum v naught. And let's just, and in this problem we stated that it's on the x equals 0 plane. So we're going to define them separated in the y direction. So in this case, if this is the x equals 0 plane, we'll have x coming out of the screen, z going up, y, and this seems to be correct because if you do x cross y, you end up with z, which is the right orientation. So we have two current carrying wires. In this case, they're going in opposite directions, separated by d. And the main question is what is the force from, let's call this wire 2. What is the force on wire 2 due to 1? Now I kind of set up a similar problem to this in our discussion of the Lorentz force, and we had this two integral, two cross product monstrosity, and I made some comment that, if we were to use Ampere's circuit's law, we could come up with a much easier way to come up with the result and find out what the force is. So let's do that right now. So the easy way, so in this case we're going to do the easy way using Ampere's circuit law. So first of all, let's start with knowing remember the key thing, if you don't want to do it the hard way is just using the Lorentz force equation. The Lorentz force, F equals QV cross B. I think I actually used a capital letter Q. And then this expression had a current, that expression had a current. You had two integrals, some cross products. It was a couple cross products. It was really ugly. So I said that in many cases, if you have two currents involved, the way to go about it is to find the magnetic field for one expression first. If you have a simple expression for the magnetic field, then you can plug it in this and approach it. You have one less cross product and one less integral to deal with. So we're going to find H first. Now recall from past discussions, the solution for if you just have an infinitely thin current carrying wire is going to be equal to 2 pi, I over 2 pi rho, where rho is the distance from the current to the point of observation, and it will be in the phi direction. So for current, for line 1, so current 1. Now let's just evaluate this for current 2 at location P over here. So remember these forces, if you use the right-hand rule, this current is going to result in a magnetic field that's going this direction. And then this current is going to give a magnetic field that goes in that direction. Again, use your right hand, point your thumb in the direction of the current and see what direction your fingers curl. And so using that, we can determine what the field is. So this is the field due to current 1 at location P is going to be what? So it's going to be I over 2 pi. What's the distance? The distance is d. And if we were to convert this to Cartesian coordinates, what direction would the field be going? So if you have your thumb pointed here, the field is going in this direction, and when you're right here, the field is actually going to be going into the screen, right? Which is the negative x direction. So by just looking at it and using your knowledge of what the field for a wire is, you know that the H field that is experienced at point P at this wire is going to be I over 2 pi d in the minus x direction. So now you have a simplified expression that you can put into your Lorentz force, right? So for a short segment, for an infinitesimal segment of current at location P, the force that you're going to experience is going to be equal to I, that's referring to this I over here, dl, because we're just looking at a short segment of length P, cross the B field, right? And the B field in this case is going to be equal to mu naught I over 2 pi d, because it's the H field times mu, right, in the minus x hat direction. In this case, dl, what direction is the current going? The current is going down, right, which is the negative z direction. So dl is going to be dz in the minus z hat direction. So now we just have to plug this in and do an integral. So if we do the cross product of the unit vectors, so we have minus z cross minus x, so minus z cross minus x is going to be equal to minus y, if you work through it, or it's going to be equal to plus y, apologies. So then you're going to have mu naught, the i's are the same in this case, so we're going to have mu naught I squared over 2 pi d. We're going to pull out the constants. We have our dz. We have our dz, it's going to give us the y direction. So now we can integrate both sides, and we get that f is going to be equal to, pull out the constants, mu naught I squared over 2 pi d, integrate across this this length. Well, I didn't specify, but let's just say the force due to a line of length L. We'll just a length segment of line L, so we'll just integrate from z equals 0 to L dz. So now if we do the integral, this is just going to be equal to L. So you have mu naught I squared L over 2 pi d. And if you wanted to express it in terms of the force per unit length of the current L, it's going to be mu naught I squared over 2 pi d. So if you take a look at the Lorentz force painful approach to arrive at the solution, you will see that you also arrive at this. But in this case, the main lesson is that if you use Ampere circuit law to come up with a way to find the magnetic field in a closed form solution, you can then, if you just write it in terms of magnetic field, instead of using the Biot-Savart law to calculate the magnetic field, but if you use some kind of simpler form, you can come up with a much easier expression to arrive at the Lorentz force. And in this case, since these two currents are going in opposite directions, and the answer F is in the positive. Oh, I lost the vector in there. But F is in the positive y direction. So are these wires attracted to each other, or are they repelling each other? Right. So if this experiences a force in the y direction, they're repelling each other. And so there you have it. You have now figured out what goes on in the inner feelings of a current carrying wire in the presence of another current carrying wire going in the opposite direction, a strong sense of repulsion.